Yeah, today's problem is Yusuko Silver 2016 The Open Contest, number 2. And it's called Diamond Collector. It's not shown here, but yeah. So the problem is basically what it's saying is Bessie has a bunch of diamonds, n of them, and n is less than or equal to 50,000. And the diamonds have sizes. And she's basically trying to put as many diamonds as she can into 2 different cases. And in each case, like within a case, the diamonds can't be too far apart in size. So in particular, they have to be within K of each other. Okay, so yeah, we're gonna input K and N, and then a bunch of sizes of the diamonds, and we're trying to output the largest possible number of diamonds that we can get. So the first thing that we're going to do is pretty intuitive because we're looking at the relationship between the sizes of a bunch of different diamonds. So the first thing we're going to do is sort them by size. So in this example, these are the diamonds. So if we sort them, it's going to be 1, 5, 5, 9, 10, 12, 14. Okay, so these are all the sizes. And basically now what we're gonna do is try to find out like how far each diamond can extend if they're the starting point of a case. So basically what this means is like if we look at 1, K is 3. So the largest diamond that can be in a case that starts at 1 is size 4. So it can only go up to here. And then for 5, we can only go up to the other 5. And for example, for 9, we can only go up to 12. So yeah, that's what this means. And there's a few ways we can do this. So if you think about a brute force way, that's basically saying for each diamond that we start at, we can go like n times to the right at most and see when it has to stop. So this is O of n times n, which is O of n squared. And this is going to be too slow because if you look at n, 50,000 squared is 25 times 10 to the 8th, which is more than 10 to the 8th because you want around 10 to the 8th at most operations in your solution. So that means we need an ON or ON log n solution. Yeah, so brute force isn't really going to work. And this is where the topic for today comes in. It's called 2 pointers. And yeah, so I'm just going to explain what that is. So 2 pointers is, in my opinion, pretty cool. I don't think it shows up as often as something like prefix sums, but it's still pretty useful. So like the name suggests, we have 2 different pointers, and they iterate through an array. And specifically, the way they iterate is monotonically. So basically, each iterator has to go always to the right or always to the left. And what this guarantees is that the number of operations they're going to take is at most O of n, because they're not going to backtrack or anything. Like, they can only go all the way through, which is n operations. So I think like the classic example of how people explain 2 pointers is if you have an array of numbers that's sorted, let's say 1, 3, 4, 5, 7, 12. And we want to find 2 numbers that sum to 9. So yeah, the way we're going to do this is with 2 pointers. One of the pointers we're going to start at the very left, and then the other one's going to start at the very right at 12. So first, 1 plus 12 is 13, which is too big. It's greater than 9. And so at this point, we know that the pointers go in the same direction always. So like if we were to move the red one, then it would have to go to the right. And if we were to move the blue one, it would have to go to the left. So if we move the red one to the right, this is going to be 3 instead of 1, which increases the sum. And if we move the blue one to the left, then this is going to go from 12 to 7. So that decreases the sum. And since 13 is too big, what we're going to do is move the blue one to the left. So now we can basically just repeat this. 1 plus 7 is 8, which is less than 9. So we're going to move the red one to the right. And then now it's 3 plus 7, which is 10, too big. So we move the blue one. And then finally, 3 plus 5 is 8, which is less than 9. So we increase the sum by moving this red one to the right. And now what we have is our solution, because 4 plus 5 is 9. So those are our 2 numbers that we wanted in the beginning to sum to 9. And we know this is always going to work because we're basically just going over the whole array. So whatever solution there is, we're going to find it. And so the basic idea of this is like we're using the previous information, like 13, 8, 10, and 8, to find our solution. Okay, so now we're going to try to see how to apply this to this problem. So if we use 2 pointers, the way we do this is we're trying to see how far one starting point can extend and do that for like all possible starting points. So if we start at 1, then we can only go to 1 because 5 is too big. So now we move this first red pointer to 5. So if we start at 5, we know that we can obviously go as far as the previous number did. Like 1 only goes up to 1, but 5 can go up to more than 1. So basically this blue thing is going to go up to the 5. And then if we move the red one, we're looking at starting at this 5 now. The blue one stays here. Okay, if we look at the 9, obviously the blue one won't backtrack because the 9 can go farther than the 5, and it goes up to 12. So hopefully you get the idea by now. Basically what we're doing is using the information from before, and like what it's saying is that the endpoint of where the case can end is monotonically increasing. Monotonically, yeah. So as we said before, this is going to take O of n because there's 2 pointers. They're only going the length of the actual array. So this takes O of n, which is good. So yeah. As a side note, like there's another way to do this that doesn't use 2 pointers, and that's in C++ equivalent to upper or lower bound. If you don't know what these are, they're basically just binary search operations where you can find like where a certain number appears, or like where the numbers become at least some number. That's probably not a great explanation, but basically you can use this to say like where does the last number that's less than or equal to 1 plus 3 happen? Or where does the last one that's less than or equal to 5 plus 3 happen, and so on. And these operations are binary search, so log n. And if we do it for n different starting points, that's going to be n log n. Okay. So now we know how far the case can extend for each possible starting point. And now what we're going to do is take that and find the maximum sum of the sizes of two cases. So we have two different starting points, and we add up their sizes. And in this part, the key is to realize that the cases shouldn't overlap. Because if we have like one case that starts here, and then another case that overlaps with it and starts here, the total size is only this much. But if we start like here instead, we're already going to have something bigger. So this is probably pretty intuitive, but it's pretty important. Yeah, so now what we do is we fix the first starting point. So in this case, that would be this one. And if we fix a starting point, then all we have to do is take the maximum of the sizes with starting point after the first case's ending point. So yeah, now we have to do this. As you can see, there's kind of a few sub-problems in this problem. So if we have to take the maximum of these, what we can look at is like we have our sizes. So if the first starting point is 1, then we want to take the maximum size of how much each of these starting points can reach. And if our first starting point is 5, then we're going to go to 9 because 5 can be included in this first 5's case. So we're starting where it doesn't overlap. And then if we look at this 5, it's the same. For this 9, we're going to start at 14. So you can see that these intervals are decreasing. And they're kind of like rooted at the end of the whole array. So this gives us the idea to use something really similar to prefix sums, which we talked about last time. But instead of sums, we're going to use maximums or maxima. Basically, we're going to keep a running maximum starting from this end and going this way. So like we're going to have the max of the size of starting at a 14, and then the max of starting at 14 and starting at 12, and then so on. Yeah, so as we saw last time, prefix sums in one dimension takes O of n to preprocess, and O of 1 to query. So we're fixing a first starting point. There's n possibilities for this. So this is going to be n times O of 1. So in total, we have O of n. So yeah, that's basically it. As you can see, our total like big O runtime, or yeah, is going to be O of n, or O of n log n if we use this thing. But I think the important thing to note is that like, as we saw in the previous problem that we did like 2 weeks ago, we're always fixing something, because if we don't fix something, then we don't have enough information to go off of. So like in the prefix sums problem we were doing, it was fixing 2 dimensions and then like finding how many ways there are to do the other 2 dimensions. Does that make sense? So yeah, that's basically it. If you have any questions, you can ask. But yeah, that was all for me.